Okay, we're live.
Hi.
Hello. All right. This one's called the logistic. I will go over this, and I'm not in any necessary order, but the logistic function, natural log, right? We didn't do. Help me help you. Natural log. LN, the LN thing. No one knows what I'm talking about. Natural log. No, Mr. Samuelis, we didn't. And then there was one more. Oh, greatest integer. Who asked that? What's that int thing? Okay, it's the silliest thing in the world. I am going to cover it though, and try to give you something that works like it in the real world, kind of, sort of. But to this one, it's actually kind of easy to fill in the stuff by the picture. It's like, what's the domain? Let me just look at it. What's the domain from this picture, this drawing? Uh-oh. All real numbers, which you've said it the right way. Knowing that you see the behavior here and here, what's the range? 0 to 1, does it include 0 and 1? No. Now I'm going to stop and actually explain. I could be wrong, and then people that listen to this movie, nobody, will say that I'm wrong. But okay, for an exponential function, you haven't. Oh, for the love of dog! Look at what just happened there. That's right when I touched the screen too, so I don't even know what I selected there. But anyway, for an exponential function, you have an asymptote, and then the graph goes like this, then it slowly grows, then it takes off, and then the growth just goes nuts at the end. All right, it still goes infinitely right and up, domain range. As x approaches infinity, so does y. But in real world, think about culture. In science, you put a bacteria into culture, right? And then what happens? One cell turns into what? 2 turns into? 4 turns into? And then it keeps going and going. If that went forever without anything to check that growth, do you know how big that bacteria would end up becoming? It'd take over the world. Okay? It would take over everything. So there's actually limits to that growth. Maybe the size of the Petri dish. Did I say that right? Petri dish. Don't look at me that way. I'm not science. Petri dish, or the amount of food that it can grow under, so there's limitations. So the logistic function, here we go, growth, but then there's something that contains the growth and levels it off. So that's kind of like what I feel the logistic function is good for. There's a little bit of exponential in the middle, but then something flattens it out at the end and controls how something could grow. Anywho, is it continuous, yes or no? Decreasing, increasing behavior. It increases forever. Symmetry. Don't be redonkulous. Boundedness. Is it bounded below or above? Both. So what do you say for that? You used to just say bounded if it was asked of you. Sometimes you could just say, in this case, boundedness, both. But bounded is fine. No extrema. No, asymptotes. Sorry. A little too fast. Y equals 1 and y equals 0. And end behavior. This is interesting. I'm just going to verbalize it because I don't feel like writing. The limit as x approaches infinity. As x approaches infinity, what does y approach? 1. As x approaches negative infinity, what does y approach? 0. So you can write those limits down. I said it as Algebra 2 questions. You know how to do the limits. You can handle it. All right, so let's move on. We did sine, cosine. We talked about those. E to the x. Oh, darn. I have my work from last time still up here. My bad, dogs. So I'm just going to explain it. Remember when I said E is, what is E? E is 2 point, come on, someone remember? 7, 1, 8. Everyone just throwing numbers at me, and they hurt. All right. So instead of 2.718, it's okay to graph 2, and then you kind of get a close representation for this. So I apologize that we didn't talk through this together, but look at this chart. Look at what I have down here. ln of x is the same as log base e of x. So y equals log base e of x. And then my students from last year, what does that mean? I'm going to do this logarithm so I can see how it graphs. I'm going to change the log to a what? Exponential scenario. And I have a nice little PowerPoint video that I videoed that you'll get to hear that in Chapter 3, those that are not in the loop right now. So, yep. All right, so E is the base, Y is the exponent, and X is the what I call the answer position. And that's all a logarithm was. It repositions the situation. So I want you to write this and write this, because even if you didn't have me last year and you didn't get that sound, you were still supposed to know that, how to change a logarithm to an exponent. And the reason I did that is then we could kind of come up with coordinates, but we can plug in for y and then solve for x and then plot the points. And then from that we can make a generalization of what the graph looks like. And that's what we did last year. Whether we remembered it or not, and we only did it like one day, I think, maybe two tops. It's one of those, we skimmed over the thing. This year it's going to be a little bit more in depth. So what happens when I plug in 1? Oh, and then what I did is not e, let's just do 2. 2 to the y instead of e to the y. Because this is the same as graphing log base 2 of x equals y. All right, so if we graph that, we're close enough to what log base e is. So what happens when I plug in 1 for y? What's 2 to the first, everybody? Answer the question. What happens when I plug in 2 for y? 2 to the second is 4, but this is how it works. 2 in for y gives me 4 for x. The coordinate that exists is 4, 2, and I have that graphed up there. And then I can plug in 3, 4, 5, 6 for y. What happens when I plug in those numbers for y? What happens to x? It gets really big. So the domain and range go off, as x approaches infinity, so does y, even though I'm plugging in for y to solve for x. But what's interesting is what happens the other way. First of all, anything to the 0 power is what? Anything to the 0 power is what? So when I plug in 0 for y, you can look at the chart yourself. I get 1, but that means 1, 0 is a point. Then it gets real interesting. What happens when I plug in negative 1 for y? 2 to the negative first is 1 over 2 to the first. 2 to the negative 10th is 1 over 2 to the 10th. Now watch my pen to graph this coordinate. I am at 0, 0 right now. Okay, and I can't stop shaking. I think it's the coffee. Here is 1 over 2 to the 10th to the right. Bloop. That's actually even too far. It's even not that far. Comma, negative 10 all the way down here. So what are you never going to get for an x value? You're never going to get what for an x value? 0. So what do you have? You actually have an imaginary line that you draw yourself. That's what an asymptote is. It doesn't really exist on the graph. You do it there as a boundary. You do it because you're annoyed that you had to plug in negative 10 for y and then get 1 over 2 to the 10th for x, and I have to keep doing that. No, you don't. But what you do have to say is there's a boundary that this graph will never cross in this case. So a logarithm has a vertical asymptote like this. All of them do. So you can see all the stuff that I have over here that really affects the domain then. And then the range still goes from negative infinity to infinity. And I think all the rest should make sense. You do have a vertical asymptote here, and there's only one limit that matters. The limit as x approaches infinity, which is infinity. What do I hit? I forget what I'm doing. There we go. Don't just be like copying like a little copier right now. Do listen real quick. And then actually this used to work back in the day. How many people have a cell phone? On you? Illegal. All right. So cell phone packages back in the day, like in the 90s when I got my brick phone with a big battery attached to my side, it was per minute, believe it or not. I got no package. It was like I paid per minute. There was a lot of big phone, bills back in the day. But what happens? What does the phone company do when you call and you talk for 1 minute and 1 second? What do they really charge you for? 2 minutes. What happens if you go for 59 seconds? What do they charge you for? 1 minute. 1 minute, I almost said 99 seconds again. 1 minute and 59 seconds. What do they charge you for? 1 minute and 1 second. 2 minutes. They charge you for 2 minutes. That's the way they did it back in the day. Okay, so what I'm showing you up here is kind of the very similar to that. Back in the day when I had a cell phone, I had like $20 monthly charge, and then I paid per minute after that. So automatically I started at $20. All right, so let's say that's $20. All right, and then when I made one phone call, all right, and then let's say this is minutes on the x-axis, 1 minute, 2 minute, 3 minute, so on and so forth. Or if they just added up the time, after a month, if I called for 0 all the way up to, let's say 1 second, all the way to 59 seconds, and this is 1 minute right here, let's say it was $1 a minute, which is ridiculous. I just want to make this easy. So here's $21. What I'm doing is trying to graph this function and then show you how this relates to what the greatest integer actually is, which is a weird concept. So at $21, I need an open dot there, because if I don't call at all, I owed them $20 for owning the phone. It was a monthly charge. But soon as I did 1 second, all the way up to 59 seconds of calls, then actually 1 minute, 60 seconds, I would owe $21. So this little graph right here shows me if I called 1 minute, I owed the company $21. And then what happens at 1 minute and 1 second? What did I owe them? $22. So here's 22. I would need an open dot here because at only 1 minute worth of phone calls, I'm being charged 21, not 22. But why the open dot there? Because I have to account for anything just past 1 minute. The best way to do that is put an open dot there, then continue from there. And I could do this forever, right? And that's how I used to get charged for my phone bill. It wasn't 1 minute a phone call, but you get the idea. So what's the greatest integer? It's the most ridiculous word I've ever heard. The greatest integer of a number is the smallest integer that number is in between. Now I probably just butchered that. But 4.6 I have as an example up there. What is 4.6 between? What two integers is it in between? 4 and 5. The greatest integer of 4.6 is 4. I have no idea why they call it the greatest integer. In my mind, they should call it the least integer. What integer is it? The smallest one that it's in between. So 4.6 actually graphs to 4. 4.6 is my input value. 4 is my output value. So 4.6 comma 4 is a dot right there that I just put. Then what's the greatest integer of 4.9? What's 4.9 between? 4 and 5. Which one's smaller? Well, it's just what you do. And I'm not going to tell you that I understand it myself. I just know what it is. I'm just the informant. So don't yell at me. 4.9 comma 4. But then what happens when you go to 5? What's the greatest integer of 5? 5 isn't in between anything. The answer is 5. So what do I have to do? I have to step off. 5 comma 5 is a point. So why do I have an open dot right here? Because I could have done the greatest integer of 4.9999999999999. And what's the answer to that? What's the greatest integer of that annoying decimal? 4. So that's why we put an open dot there, because, all right, it's not 5 comma 5, but right up to it, there are points that I just can't really show very well, so I put an open dot on there to show that that's where the step off is. And then, what's the greatest integer of 5.999? Still 5, so that's the next rung. Greatest integer of 5.9 is still 5, and then the next step off. So this goes forever. This little pattern. A couple things are really tough to answer about this, but domain and range are not. Domain is, I'm stuck, all real numbers. Range, the best way you could say it is it's only integers, because that's what you're getting as output values. You're only getting integers, which are positive, negative, whole numbers, or 0. Okay, well, whole numbers include 0 as well, if you know that term. Increasing, decreasing behavior. What is the only behavior that's listed up here? What kind of behavior is this in intervals, infinitely? Not increasing, not decreasing, but what? Every single time. Constant on each rung. So there's a whole bunch of infinite constant intervals. From 0 to 1, 1 to 2, 2 to 3. I'm not even writing it. Okay, not even going to do it. There's no symmetry, no boundedness, no extrema, no. Then end behavior is really tough to answer as well, and I don't think it really applies to this little question. But as x does go to infinity, what are you going to get as output values? Integrals or integers that are actually going off to what as well? infinity, so I guess you could actually answer that, but it's just kind of strange on this. It's usually best for curves and then behavior. Now for something completely different. This happens a lot. Okay, so within section 1.3, so again, I'm legally staying with the book and staying in order. The book does the 12 functions in 1.3, then it throws at the end piecewise functions, which, by the way, the greatest integer function does have like a lot of pieces. Hey, the phone example that I just said, there's pieces to that graph depending on certain parameters. If I don't make a phone call, I was charged $20. If I make 1 second to 59 seconds or 60 seconds of a phone call, then I was charged $21. And so on and so on and so forth. Piecewise functions are one function. What's this function called? What's that function called right now? F of x. But it's defined by different pieces, defined by different intervals. Back to the phone call example. One interval is no phone calls, $20. Next interval, 1 second to 60 seconds, $21. Next interval, 61 seconds to 120. I couldn't think of the seconds. 120 seconds, $22. And that goes on forever if I had a whole lot of phone calls. Now, I never understood why students have a problem with this, because it's actually real basic, real simple what you do. All right? And what you do is you understand that I have to graph this under these parameters. So the first thing that I always do with my students is, okay, pull that out individually. So I have to graph f of x equals 1, and I can only graph them underneath these x rules. So what does that mean? Old school graphing. I can plug in the chart for x. Just tell me, what can I legally put in there? There's the bell. Means this function, f of x, is defined as f of x equals 1 only for values of x that are less than or equal to -2. So if I physically were going to do that by hand, then these are the values I can only legally plug in. And I can keep going. -5, -6, -7. What does that mean this graph is going to have on it? Starts with an A, and you shoot it with a bow. Arrow. An arrow. Because there's a start here. So what happens when I plug in -2? What do I get? This is weird. Get nothing out of 4th hour. It's like a Morgan here. 1. -3. What do I get? Maybe they all had lunch. 3rd hour. What's -4? This is a picture of a horizontal line. Okay, so what do I have to do to start this off? I start at oh, I'm caught again. This is dangerous. -2, 1. -3, no, I know that's a horizontal line, and I have to graph it only for x's that are less than or equal to 1. So it's a horizontal line only up to here. All right, now I'll tell you what the crazies did last year. They looked at these, they looked at all 3 pictures and drew all 3. So the one thing is they drew this horizontal line, then they drew this, and then they drew this, and then their picture was just a whole bunch of graphs crossing each other. I will tell you right now, if you do that this year, your head will be spinning so quick, because I screwed it up, I'm out of practice. I will mark you wrong so quick your head will be spinning. That is an absolute abomination as far as what a piecewise function means. You'll be doomed. All right, did I say good morning, by the way? I think I did, but I'll say it again. Good morning. Next, f of x equals. So I got to get my eraser here. Yep, I erased my back. Oh, I'm so out of practice. Oh, for the love of dog. Okay, how do I get it? All right, good thing this is taped. All right. Now I graph this. What is that a picture of, by the way? A line. Okay, then what can I plug in -2 then into this line? Yes or no? No, so what should I start with? Should you, though? Okay, what did you say, sir? Did you raise your hand? Okay. What should I put then on this chart? Should I put -2? Is that what you're saying there, Chief Aruni? Yeah. And then what do I get when I plug in -2? What do I get? 0. Now, what do I put for -2, 0? I'm not allowed to actually plug it in. I'll tell you why you actually do have to plug it in. And this is mistake number 2. Those that do have an idea of how to do a piecewise, This is the biggest mistake. Starting with -1 only because they don't think of a decimal. They only think integers exist. And then they actually miss an infinite amount of coordinates. But let's move on. When you plug in -1, you get what? No time, 1. When you plug in 3, can I plug in 3, by the way?
Yes.
And what do I get when I plug in 3? 5. So I'm going to go 3, 5, and I know this is going to be a line, 2, 3, 4, 5. But those that do this wrong start with -1 and only give me this chunk. And then what they miss is an infinite amount of coordinates between those that open and that close dot. So that is not what can happen. You need to understand that. Let's just put it this way. I could have plugged in -1.99999. Did I do that right? Yes. So I could have plugged in -1.999 for x and get an output value. So I got to account for that with an open circle. So this dot's not needed there. I was just doing that for a point. Let's move on. Last thing is, let's go to purple. F of x is defined as this. I didn't finish the blue one. 2 plus x. That's supposed to be blue. Deal with it. And then, I think I'm over-explaining at this point. Do I plug in 3? Yes or no? What do I put at 3, 6? Open circle. 1, 2, 3. 1, 2, 3, 4, 5, 6. And then, you know what I could do? It's a slope of 2. So the other points I could just do by line ideas. Okay, so there's your piecewise function. One function defined by 3 different parameters, let's say. Whatever that means in the real world, figure it out. We're not real world in this. We're just kind of getting the wax on, wax off idea behind it. But are there points of discontinuity? Yes or no? What kind of discontinuities are these both? Jump. Where are they located? Well, that's pretty simple. You have a jump discontinuity at -2 and a jump at 3. Just going because, it's not that bad. So, number 1, super fast. Then I'll have you work on the third one and we'll talk, and I'll just show the answer online. Not that I have anyone absent, but. All right, so what can I plug in? Do I plug in 0, yes or no? By the way, what should this be a picture of? You should think about these things. Ultimately, if I graph the whole thing, it'd be a picture of a what? V. But I'm not going to argue with you. Why is it actually a line? Yeah, so it actually has one part of the V, which actually ends up being linear. So this is 0, 0. What do you put at 0, 0? Open dot, and then -1, -2, 1, 2. That's why he may have said line, because we cut off part of the V based off of the parameters. And then you go to this. What's this a picture of? And actually, in your piecewise functions, you better be asking yourself those things before you start going to a chart. What is it? Maybe where's the vertex? What parts of this am I going to be seeing? So expectations of picture. And by the way, all this should be done without a calculator. This is on your no calculator part of the quiz on Friday. Oh, wait a minute. What happens that's special? So the one that I could plug in, 0 for x, I ended up getting what? What did it do to this whole of the other graph? It patched it, if you will. And then 1, 1, and then 2, 4. So I ask you, is this graph, g of x, continuous? Yes or no? It actually is, because they connected with each other. So there is no point of discontinuity in this special situation. Okay, last, I'm going to pause the video and have you do this. That's a Samuelus one, but it's going to be frozen for you. All right, so this first one, I'm going to graph this, and I'm being cryptic here because the students are doing this themselves right now. All right, that's a picture of a you-know-what, and you know that I can only put in these points. But should I put in this point? I think you should. Then you should make it this kind of thing. There you go. Not showing up. It is showing up, you bums. I thought I turned that off. Sorry. There we go. Okay. Now they can't see what's going on in class. And then these, actually I wouldn't even do this. I just use this idea. Okay, then this next thing, we better know what that kind of picture should look like. So have an idea what it is. And then actually, if you wanted, and it was a no calculator question, which it is going to be, Just think about plugging these values in and think about where this is for that. And that would be because of this little shift there at that position. And then this point, I am able to plug in. It's that kind of dot. And then I'm just going to plug in this one. The last one. And that's going to be, you know what kind of dot. So, I think it's all the way up here. And then get it to look like what it's supposed to look like. Kind of missed that point, but ugh. Let me redo that one. There we go. Supposed to look like that picture. And the last one. This is actually in one of those pictures. And that is supposed to be and I can plug that in. So that's one of my chart values. So having an idea of what this picture is and what the pertinent information for that picture is, so you know what's going on. I can plug in this. I believe when I plug that in, 1 minus, I think you get that for that plug-in. How many people are done? Raise thy hand. Then I know there's some symmetry here, so I know that's going to be the other point, and that's the finish of that picture. Okay, done.